Hello. In this lecture, we will cover centripetal acceleration, non-uniform circular motion, centripetal force, and then we'll look at some application of centripetal force. In kinematics, we have talked about acceleration, and we looked at the cases when the object is speeding up or slowing down, which would both result in acceleration. Now, the third case where we can have acceleration is when the object is traveling at a constant speed, but the direction of the velocity vector is changing. So an example of that is if you have an object that is going around a curve. That will also result in acceleration. So we could have a case where the magnitude of the velocity vector is changing. It could be increasing or decreasing. And then the second case is when the direction of the velocity vector may change with time, but the speed is constant. So that is the magnitude of the velocity is constant, but only the direction is changing, which will also result in acceleration. And the third case is you could have both of this. You can have an object that is speeding up, but also going around a curve. So uniform circular motion occurs when the object is traveling along a curved path with constant speed. From our definition of acceleration, we know acceleration is change in velocity over change in time. And if so what we want to here find out is what is the change in velocity vector pointing at when there is acceleration. So delta V is equal to V final minus V initial. So I picked 2 points. Let's say this is V final and this is V initial. When the object is going in a curved path, the velocity vector will be tangent to the curve at that particular point. So here the tangent to the curve is in the direction that's shown here. And at this point, the tangent to the curve is in the direction that's shown here. So another way I can write V final minus V initial is if I say V final plus negative V initial. Right? So V final is my vector, which is, let's say, along the pointing towards the left, and V initial is my vector that is pointing somewhat like this. So a negative of V initial vector is going to be a vector that is just flipped. Okay. Now we have dealt with in earlier section with how to add vectors. So graphically, you would place V final and then you bring the tail end of V initial and line it up with the head of V final. And then the change in velocity vector or the addition of these two vectors will be pointing from the tail of V final to the head of V initial, and that which is our acceleration. So as you see, the acceleration is going to be pointing downwards at this point up here. So when the object is traveling in a curved path, doesn't have to be a full circular path, it just have to be a curved path, it will undergo acceleration towards the center of the curve. The magnitude of the acceleration is equal to the speed square divided by the radius of that curved part. So here, as you can see, here is the acceleration. This is just giving us the magnitude of the acceleration. To determine the direction of the acceleration, you'll just have to look at um, the point. So for example, at this location, acceleration is towards the center, which is at an angle. At this point, the acceleration vector is pointing straight down. At the point over here, when the object is at this point, then the acceleration is going to be to the right. The object is at towards the right, then the acceleration is going to be towards the left. So the general idea is the acceleration is going to be pointing towards the center of the curve. The direction of the acceleration is perpendicular to V at all points. You can see it here. It's going to be perpendicular. At this point, it's going to be perpendicular. So let's look at an example problem. Here, the problem states that we are assuming that the Earth's orbit is nearly a circle. What is the centripetal acceleration between Earth and the Sun? Take the distance between Earth and the Sun to be 1.5 times 10 to the 11 meters. So we have just introduced the centripetal acceleration equation, which is A centripetal is equal to V squared over R. So if I know V, I can calculate, and if I know R, I can calculate the centripetal acceleration for the Earth. However, as you see here, we are not given V, we are only given R, which is 1.5 times 10 to the 11 meters. So, well, how do we determine V? Okay, so there's a couple of things we can do. One is we can say, okay, how long does it take for the Earth to go around in this circular motion, which we know is about 365 days, which you'll need to convert it into seconds in order to use this equation. For path length, this is just a circular path, and a circumference of a circle is given by 2 pi r. So the information that I do have is r. So t is something that I know because of my experience on living on Earth. So substitute that into the equation, and I'm going to simplify. You can see, we have r squared on the top, r on the bottom, cancel out one of the exponent, and this is the simplified version. Now I can plug in the numbers because the only thing I need to know is r and t. Well, r I know, t I just need to calculate it in terms of seconds, and the centripetal acceleration comes out to about 0.00595 meters per second square. So this is the acceleration of the Earth towards the Sun as it orbits. Circular motion does not have to be at a constant speed. A particle can travel in a circle and speed up or slow down, showing an acceleration in the direction of the motion. If the speed of the particle is changing as well, then we need to introduce additional acceleration in the direction tangent to the circle, which we will call tangential acceleration. Now in this diagram, you see tangential acceleration vector, and this is the centripetal acceleration vector. So the net acceleration of this object is going to be at a diagonal, which is shown here. And now this vector is determined by parallelogram rule, or you can also use Pythagorean's theorem to determine the hypotenuse of this. And you can see that tangential acceleration is always at a 90-degree to centripetal acceleration. To figure out the tangential acceleration, we'll use our definition of acceleration, which is acceleration is change in velocity over change in time. And therefore, the total acceleration in terms of vector, this is centripetal plus tangential. In this example, we're told that there's a particle that moves in a circle of radius 2 meters. During the time interval from 1.5 seconds to 4 seconds, its speeds varies with time according to this equation. So v as a function of time is equal to 4 minus 6t to the negative 2. What is the total acceleration of the particle at t is equal to 2 seconds? We know that this object is, its velocity is varying. So we need to determine the centripetal acceleration, and then we need to determine the tangential acceleration. And with that, we can calculate the net acceleration. So to find the centripetal acceleration at t is equal to 2 seconds, we can plug the time, which is t is equal to 2 seconds, into our velocity function, and we can determine the speed of the object at that point. And once we have that, then we can square that term and divide that by the radius, which is 2 meters, and we'll get about 3.1 meters per second square. To find the tangential acceleration, we'll just have to take the derivative, time derivative of the velocity function, which ends up being 12t to the negative 3. We can plug in the time of 2 seconds, and that comes out to about 1.5 meters per second square. And now to find the magnitude of the acceleration, as you know, these two vectors are perpendicular to each other, so this is a right triangle, and you can apply Pythagorean's theorem. If you don't see it, here's a little diagram showing here that the tangential acceleration is in this direction and centripetal acceleration is 90 degrees respect to the tangential. So we're looking at this diagonal part, which is just going to be 3.1 square plus 1.5 square, and then take square root of that, which comes out to about 3.4 meters per second square. To find the angle, well, you have to think about what angle are we looking at. Well, if we are trying to determine this angle here, then tan inverse function, we're going to use tan inverse function. So tan inverse function is going to be opposite over adjacent. Opposite is 3.1, adjacent is 1.5, which comes out to about 64 degrees. When an object is going around in a circular path, it will experience acceleration, which is called centripetal acceleration. This centripetal acceleration is due to centripetal force. The direction of the centripetal force is always towards the center of the curvature. And the centripetal force will always be perpendicular to the velocity vector, as shown in this diagram. If we apply Newton's second law, we have F net is equal to mass times acceleration. For a uniform circular motion, the word uniform circular motion implies that the speed in which the object is traveling in a circular path is constant. However, the direction of the velocity vector is changing. Since there is change in the direction of the velocity vector, there will be acceleration. So for uniform circular motion, the acceleration is going to be centripetal acceleration. The subscript of c here represents centripetal. And this acceleration is equal to v squared over r, where v is the speed or the magnitude of the velocity vector and r is the radius of the curved path. This is called the centripetal acceleration. Now taking this acceleration and applying it to Newton's second law, then we have the Newton's second law that force centripetal is equal to mv squared over r. Let's look at an example with centripetal force. It says you have a child of mass 40 kilograms is in a roller coaster car that travels in a loop of radius 7 meters. At point A, the speed of the car is 10 meters per second, and at point B, the speed of the car is 10.5 meters per second. Assume the child is not holding on and does not wear a seat belt. What is the force of the car seat on the child at point A? Okay, so let's start with A. We'll go back to the other later. Alright, so anytime you have these dynamics problem, you want to start with a free body diagram. Now at point A, I will draw out my little diagram. I'm going to simplify it as much as I can. I have a little cart. It's something like this. And I'm going to draw out the forces that are acting on a person who is sitting inside. So let's say there's a gravitational force, just straight down, that's mg. Right? And then there's going to be a normal force. Normal force in this case is going to be perpendicular to the surface, so it's going to be pointing downwards as well. This is the normal force. There is no other force that are acting on this object. Alright, so we'll take this diagram and we will apply Newton's second law, which is F net is equal to ma. In part A, they're asking us to find the force of the car seat on the child, which is the normal force. So we are trying to solve for the normal force. Now, since this motion is a circular motion, we have F net is equal to mass times centripetal acceleration. All right, so net force, I have normal pointing downward, so negative, plus gravitational force pointing downwards as well. That is equal to mass times centripetal acceleration, but the direction of the acceleration is also downwards, which is towards the center of the curve, and that happens to be downwards at point A. So it's going to be, it looks something like this. All the negatives can be canceled out if you divide both sides by negative. And then we can solve for the normal force, which is just going to be normal is equal to mass times centripetal acceleration minus mass times gravity. Well, centripetal acceleration, we have an equation, which is v squared over r. So substitute that in. And then we can plug in the numbers. Right, so this mass is 40. Speed at point A is 10.
R is 7 minus mass is 40 times 9.81. So when you calculate that force, it should come out to about 179 newtons. Part B of this problem is left as an exercise to do on the homework. Let's look at part C. Part C states what is the minimum speed that is required to keep the child in his seat at point A. So we look at the case when the child has just lost contact with the seat. So again, at point A, you have this cart, and the forces that are acting is going to be the gravitational force. Since the child has lost contact with the seat, he no longer have normal force on him. So applying Newton's second law, which is F net is equal to ma. Again, we're applying this in the vertical direction. So net force is going to be the gravitational force pointing downwards, and then mass times centripetal acceleration, which is also going to be negative. Divide both sides by m, divide both sides by -1. We're going to solve for v. V is equal to g times r. Then it's the square root of that. So plugging in the numbers, you have 7 multiplied by 9.81, and then taking the square root, which comes out to about 8.23 meters per second. Let's look at another example. It says calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at a speed of 25 meters per second. Assuming an unbanked curve, find the minimum static coefficient of friction between the tires and the road. Static friction being the reason that keeps the car from slipping. So this is the diagram. And I have drawn the normal force, which is perpendicular to the surface. Then we have the gravitational force, which is straight down. And then we have force of static friction, which is towards the center of the curve. Friction is towards the left because it is keeping the car from slipping. And because it is the only horizontal force acting on the car, friction is equal to the centripetal force. So Newton's second law, F net is equal to ma. Well, this is going to be centripetal acceleration, and we're applying this law in the horizontal direction. So net force is force of static friction. This is equal to mv squared over r. Okay, so force of static friction can take a range of values from 0 to its max. Let's look at force of static friction at its max. So the maximum value of static friction is mu sub s times the normal force. In a horizontal surface, the normal force is equal to the gravitational force. So normal force in this case is m times g. The m cancels out, and we are asked to solve for mu sub s. So mu sub s is equal to v squared over r multiplied by g. Plugging in the values, so v is 25, r is 500, and g is 9.81. This coefficient is 0.127. Coefficient of friction don't have any units. One thing you should note that this coefficient of static friction does not depend on the mass of the object. As you see, the mass is canceled out. It only depends on how fast the object is moving and the radius of curvature. Let's now consider banked curves, where the slope of the road helps you negotiate the curve. The greater the angle, the faster you can make a curve. You might have looked at a race car track, and you should note that on the race car track, the road is at a slope. And they do that because of that slope, it helps drivers make a turn at a high speed. So banked curves are where the roads are at a slope, just like in this diagram that is shown. In an ideally banked curve, the angle is such that you can negotiate that curve at a certain speed without the aid of friction between the tires and the road. So let's draw out our free body diagram. Let's look at an example. This is a scenario. You have a car that is making a turn on a sloped road. We have a normal force that is perpendicular to the surface, as shown, and then we have the weight, which is the force of gravity. The angle that the road makes, this angle over here, theta, is equal to the angle here. Now, when we looked at forces on an object that is sitting on an inclined surface, right? One of the trick that we have used was we rotated our x and y axis. Now, this problem can be done in that way, but it is easier to leave the x and y axes such that the x is along the horizontal and y is straight up. All right, so now let's apply Newton's second law. We have F net in the y direction is equal to mass times acceleration. Remember, y direction is this direction. The car does not sink into the road, or it doesn't fly off. So that's why we have that F net in the y direction is equal to 0, because there's no acceleration in the vertical direction. So I have gravitational force, which is pointing downwards, and then I have a component of the normal force that is pointing straight up. So I have n cosine of theta, which is equal, n cosine of theta minus mg is equal to 0. There's a middle step that is missing here. And then you solve for the normal force, then you can get that normal times cosine of theta is equal to mg, and then normal is equal to mg divided by cosine of theta. Now let's apply the same concept, but in the x direction. In the x direction, we are going to have centripetal acceleration. So I have F net in the x direction is equal to mass times acceleration, and this is centripetal acceleration. In the x direction, I only have a component of the normal force, which is n sine of theta. So I have n sine of theta is equal to mv squared over r. The normal force, as we have noted on the left, is equal to mg divided by cosine of theta. I can substitute that in. The mass cancels out. Sine over cosine is tangent. And if I were to solve for the speed, I get that the speed is equal to square root of gr times tangent of theta. As you note that in this equation of the speed, it is independent of on the mass of the object. So it only depends on the radius of curvature, and it only depends on the angle. Let's go over this example problem. The problem states curves on some test tracks and race courses, such as Daytona International Speedway in Florida, are very steeply banked. This banking, with the aid of tire friction and very stable car configurations, allow the curves to be taken at very high speed. To illustrate, calculate the speed at which a 100-meter radius curve banked at 31 degrees should be driven if the road were frictionless. Okay. Well, in the previous slide, we have derived an expression for the speed, which we noted only depends on r and only depends on the angle. So we're simply going to use that equation. Well, in that equation, we know that the setup was that such there's no friction. So in this problem, we are considering the track to be frictionless. So taking that equation, plugging in the numbers, you should get an answer of 24.4 meters per second. Now, if there was friction, that friction will enable a vehicle to take the curve at a significantly higher speed. That 24.4 meters per second is about 165 kilometers per hour or 103 miles per hour. So with friction, they can make that turn at even higher speed.